Welcome to Climate Feedbacks. Today we're going to be talking about how deep sea carbonate chemistry helps to stabilize global climate. So we've learned about phytoplankton and how organic matter is comprised of inorganic carbon that is fixed into organic carbon through photosynthesis. And you know that there are some plankton that make different kinds of hard parts or shells. For instance, diatoms that make opal shells, or radiolaria that make opal, or what we're going to be talking about today, coccolithophores or foraminifera that make calcium carbonate shells, either calcite or aragonite. Those are two different types of calcium carbonate. So these make calcium carbonate shells, and that can be really important both for global climate as well as ocean chemistry. And here's just some pictures of what these look like in a scanning electron microscope. So coccolithophores make these plates, these little circular liths that cover the coccolithophore, and these can act as a kind of protection. Foraminifera look like these little popcorn kernels. What you're looking at in both of these are the calcium carbonate shells. So calcium carbonates are formed in the surface ocean and can be preserved at depth. So we've talked about the biological pump, where inorganic carbon, here written as CO2 plus water and nutrients, through photosynthesis produces organic matter formation. What we're going to be talking about is just CH2O as our example organic matter molecule. So produce organic matter and oxygen. In the surface ocean, photosynthesis typically is greater than respiration, so you're making organic matter, and some of that is going to sink out. Either the plankton are going to die and sink, or they'll get eaten by zooplankton or fish, or something is going to cause that organic matter to sink out in one way or another. So at depth, that organic matter is respired and returned. That organic matter is respired back to inorganic matter and nutrients. That's a biological pump. Now there's also calcium carbonate formation. Let's say you've got coccolithophores or forams. Those are going to take calcium and carbonate ions and make calcium carbonate. And so in the surface, there's enough carbonate ion around that it's relatively easy to make calcium carbonate. As those carbonates sink, they become more likely to dissolve, but some of them will be preserved. So there's some dissolution going on at depth, just like respiration, but in areas that are not too deep, they can be preserved. And so that's how you get carbonates in sediments. So in this diagram here, it's a little bit older, but you can see that there's this dashed line above which you get this quote-unquote marine snow, which is just calcium carbonate that is accumulating in the sediments. And so above that, there's formation and settling of calcium carbonate. Now you can still have dissolution, but overall the settling outpaces dissolution, and so you have accumulation of carbonates in the sediments. Below this dashed line is where dissolution is occurring faster than settling. And this is the so-called carbonate compensation depth, or CCD. And it occurs in the deep ocean because calcium carbonate is more soluble at lower temperatures, it's colder in the deep ocean, and it's more soluble at lower pH, high acidity. And so below that CCD, you have no carbonates in the sediments. And so we have our carbonate compensation depth here illustrated in this beautiful graphic as the difference between the whitish regions and the brownish regions in our little schematic of the ocean floor. What can happen is that if atmospheric PCO2, if the carbon dioxide, the partial pressure of carbon dioxide in the atmosphere goes up for, we're not going to talk about the reasons why, but let's say it goes up, that causes then the surface ocean carbon dioxide to go up, right? We talked about gas exchange and how increasing the CO2 in the atmosphere then will increase the CO2 in the ocean through gas exchange, so the surface ocean pH will go down. Now that signal mixes into the deep ocean, in some areas faster than others. Right now we're talking about geologic timescales, so really long timescales on the order of tens of thousands and millions of years. And so you mix this signal down, so the deep ocean pH is going to drop as well, and that's going to increase calcium carbonate dissolution. So this is dissolution of calcium carbonates in sediments as well as increased dissolution of that settling down. And so because you have increased dissolution in sediments, that CCD now rises up, it goes up, and so sediments that had existing carbonates in them are dissolving. Okay. Now, one of the interesting things about carbonate chemistry is that because it's somewhat complicated, it's not always easy to intuit if you change one term or another, how are things going to respond. But when you dissolve calcium carbonate, you lower PCO2. Okay, so we've raised the carbonate condensation depth. That's dissolving carbonates in the sediment, so carbonates that accumulated over a very long time frame. And then you're lowering deep ocean PCO2. And so that's going to mix back up into the surface ocean. You're increasing the pH again, right? You're going to mix back up in the surface ocean. That's going to bring surface ocean PCO2 back down, bring surface ocean pH back up, and then you're going to reduce atmospheric PCO2. So this acts as this long-term check and feedback on atmospheric CO2. And so we can just sort of go through that again. So if we start with increasing atmospheric CO2, that then acidifies the ocean, lowers pH. This increases the dissolution of existing carbonate sediments. That then brings the pH back up and carbon dioxide down, and this then reduces atmospheric CO2, and therefore sort of canceling or acting as a negative feedback on that original increase in atmospheric CO2. Now this can go in the opposite direction. If you lower atmospheric CO2, then you go in the opposite direction, and the carbonate condensation depth will drop, and you get this negative feedback that helps stabilize global climate. So, main points of this video: some plankton make calcium carbonate shells. Carbonate compensation depth is where deposition of those shells sinking out from the surface ocean is balanced by dissolution. So carbonate's more soluble at depth, and so you have some point where deposition matches dissolution. That's the carbonate compensation depth, and below that you don't have carbonate sediments. Now if you change atmospheric CO2 levels, that can impact ocean acidity, whether or not carbonates are stable at a given depth range, and so that therefore changes the CCD. And these long-term changes in the carbonate compensation depth, by then acting in opposition to whatever atmospheric signal, whether it's an increase in CO2 or decrease, help to stabilize climate.